The Meissner effect is a fascinating phenomenon that reveals the unique properties of superconductors. Discovered in 1933 by Walter Meissner and Robert Oxenfeld, it describes how superconductors expel magnetic fields from their interiors when they transition into a superconducting state. This is not just an interesting quirk, it's a defining characteristic that sets superconductors apart from perfect conductors. So, what exactly is the Meissner effect? Simply put, when a material becomes superconducting, it becomes perfectly diamagnetic. This means that the magnetic field inside the superconductor drops to zero. It's important to note that this happens regardless of whether a magnetic field was present before the transition. The underlying physics of the Meissner effect is rooted in the formation of Cooper pairs. These are pairs of electrons that bind together at low temperatures. When these pairs form, they condense into a macroscopic quantum state. This state minimizes the free energy of the material, and in doing so, it expels magnetic fields. When a superconductor is placed in an external magnetic field, it generates surface currents known as screening currents. These currents create a countermagnetic field that cancels out the external field within the material. This interplay of currents and fields is a beautiful demonstration of quantum mechanics at work. The behavior of these superconductors can be described mathematically using the London equations, which show that the magnetic field decays exponentially inside the superconductor. For the Meissner effect to occur, certain conditions must be met. First, the material needs to be cooled below its critical temperature, known as T_C. Second, the external magnetic field must be less than the critical magnetic field, H_C. If the magnetic field exceeds this critical value, the superconductor will lose its superconducting properties, and the Meissner effect will vanish. You can actually observe the Meissner effect in a lab setting. By cooling a superconducting material below T_C and placing it in a magnetic field, you can see the magnetic field lines being expelled, leaving the interior field free. This is often demonstrated through magnetic levitation experiments, where a small magnet hovers above a superconductor due to the expelled magnetic field and the opposing forces generated by surface currents. There are two main types of superconductors when it comes to the Meissner effect. Type 1 superconductors exhibit a complete Meissner effect up to their critical magnetic field, H_C. They transition abruptly from the superconducting state to the normal state when the external field exceeds H_C. On the other hand, Type 2 superconductors display a partial Meissner effect. In a mixed state between their lower and upper critical fields, magnetic flux penetrates the material in quantized vortices. The applications of the Meissner effect are both practical and groundbreaking. One of the most exciting uses is in magnetic levitation technologies, such as maglev trains, where superconductors allow for frictionless travel. Additionally, the perfect diamagnetic property of superconductors is utilized in sensitive magnetic field detectors like squids, which are crucial in various scientific and medical applications. Understanding the Meissner effect is essential because it highlights that superconductors are not merely perfect conductors. They possess unique properties that arise from quantum mechanics. This distinction is vital for both theoretical research and practical applications, making the Meissner effect a cornerstone of superconductivity.